Okay, so first, thank you to all the women in science colleagues who've worked so hard to organize this symposium. I'm super excited to see the rest of the talks, see the posters, get to meet our summer students. It's really going to be a fun morning and afternoon, and you guys did a tremendous job in putting this together. It's also a great pleasure, of course, to address our summer students and all the rest of our fellows, faculty, students, whoever may be listening in out there. I was given a couple different tasks by the organizers, thus the title of my talk, a little bit of this and that. I was asked to give a little bit of background and some of my history. And maybe that's a little bit more focused on the younger students in the group, and then give some perspective on the Martinos Center overall. Some of this I expect many of you have heard before, but again, for newcomers to the center, hopefully some of it's interesting, and we'll take it from there. Okay, so fundamentally, what we're talking about when we're talking about research, and we're all researchers here, is innovation, how we can be innovative, how innovation actually happens. So I was looking through and I came up with this nice description of what the fundamentals of the innovation process are, and I thought I'd share it with you. So here's the 5 key stages of innovation that I came across. The first is you come up with a great idea and your colleagues say, it's not really required or important. Next, they deny that your innovation is going to be effective. They'll go ahead and say that it's not really very important. They'll say that the innovation isn't really worth the effort required to adopt it. And then, of course, finally, the 5th and perhaps most important stage, your colleagues will adopt the innovation, enjoy its benefits, attribute it to somebody else, and then deny that stages 1 through 4 happened. And while you might think that this is, just a joke, maybe not even a funny one, it's surprising to what degree this kind of happens. I remember reading about the story of the Nobel Prize winner for the invention of knockout mice, something that's so fundamental to biology, and how he described that for the first 5 years after he did it, all of his NIH grants were rejected because of points 1 through 4. Wouldn't work, or it was already done, or it wouldn't be worthwhile, we wouldn't learn anything, et cetera. And of course, we now know that it's completely fundamental. Fortunately for him, stage 5 wasn't the case, and he did get credit for his work. So that then brings us to, what does it take to be innovative? What are the traits that we see in an innovative mind? And of course, there are many of these, but I'll give a few that we'll see around here. The first is the notion of what they call divergent thinking, being able to pick up unusual associations of ideas, switching from one set of ideas to another, very important if we want to be innovative. The second, of course, is to be flexible, to be able to come up with different categories or perceptions of looking at the world. If we're always looking at the world the same way, very hard to take an innovative perspective. Perseverance, you really have to stay focused on ideas and push through against the obstacles if you want to go forward. I think all researchers understand that. Somewhat surprisingly, we think of science as this very well organized event, but in fact, there has to be some preference, at least comfort with disorder. This is where ideas that other people haven't thought of come from. And so a desire to be comfortable in an environment where things are a little disorganized, where there's complexity or asymmetry, very important for innovation. And then finally, this notion of embracing ambiguity, finding unusual things interesting and exciting. All of these things are important for innovation. But as I was looking through this list that came from a website of people talking about kind of innovative and creative intellects, it reminded me of something I had learned back in med school when I was doing my psychiatry rotation. And I went back, and sure enough, if you look at the kind of key features of the schizophrenic mind, you find a remarkable degree of overlap. The notion of divergence thinking, this kind of looseness of association that we see in schizophrenics, the delusions and hallucinations as a kind of an over degree of flexibility, perseverant behavior, people that just cannot move themselves off of a given task, like somebody with an obsessive compulsive disorder. Disorganized and bizarre behaviors as a reflection of this preference for disorder and frankly, fundamental thought disorders. And I guess the point that I really want to make with this is that, sometimes it's a fine line between being crazy good at science and just being crazy. But I'd like to think that at the Martinos Center, we understand that border and can happily live on one side of it. And only occasionally cross over to the other. Well, so where does this, take me in terms of, my own career and what, small degrees of, innovations I've been able to participate in and see around me. And because I know we have high school students here, I thought I would share with you an experience I had way back when I was in high school. I was always very interested in the sciences and especially in physics. And so it was super exciting for me when I actually got to take physics. It was in my junior year. Was really excited about that. And I remember I handed in my first homework, and a couple of days later, I got the homework back, and on the homework was just the number 28 circled in red. And, it's like, I asked myself, well, what did that 28 mean? And of course, I went to the teacher and said, what does that mean? Was it 28 out of 28? That would be great. 28 out of 30, pretty good. 28 out of 100, maybe a little less good. I remember very clearly to this day, my teacher kind of looking me in the eye when I asked, what does the 28 mean? And this was his answer. It means it's not worth the paper it's written on. And then he walked away. Sam Rader. And yet, Sam was a tremendous teacher. And that simple lesson, my first homework assignment, has stuck with me because it reminded me, or maybe taught me at that time, that first you had to embrace ambiguity, right? I didn't know what the 28 meant. And with Sam, I never entirely know where I stood. He could be very supportive one day, and the next day you would get a comment like this one. But on the other hand, the maybe more fundamental lesson is that, it takes, more than being smart, or in my case, probably more of a smart aleck, to be successful. And I'm sure many of you folks have seen the quote from Thomas Edison, that genius is 1% inspiration and 99% perspiration. Not entirely sure that the percentage is exactly right, but without a doubt, the most creative people, the most productive people, innovative people work at it. Einstein said the same thing. All of these people that we think of as being tremendous innovators, tremendous geniuses, all say that the key to their success wasn't so much their brilliance, but just their the hard work and the things that went behind it. So another important lesson that I learned from that experience, going way back, is to seek out good mentors. There's a lot of discussion about the importance of mentors, and this will be true throughout your career. Of course, when you're in high school, your mentors are your teachers. Despite Sam's comment to me, he turned out to be a great teacher, and definitely inspired me to do my best, do better than on that first homework for sure, and has stayed with me. In fact, that was back in 1972, and we're still in touch. I think the important thing that I want to point out and share with, especially the younger colleagues, is that, the seek is actually an active verb. Sometimes you're lucky. I didn't seek out Sam Rader as my teacher. That's who I was assigned to. But I did kind of seek out the opportunity to connect with him and do things with him and stay connected to him. Later in my graduate career, I actually had to seek out mentors. When I was in college, I was interested in astronomy, and I was an astronomy major, and was assigned to work with one professor, very nice professor, doing excellent work. He was very generous in his time, But his work really just wasn't for me. It was very mathematical, frankly, more mathematical than I had the skill for. So fortunately, in talking to other people, I found this gentleman, Jim Moran, who is actually a radio astronomer and who's kind of observational astronomy, you know, actually getting down, mixing up with the instruments and taking images and then thinking about how to analyze them actually kind of suited me extremely well. So gravitating to him, building my relationship with him turned out to be super important and an awful lot of fun. Interestingly, you know, my first set of experiments wasn't in astronomy, which of course, that's what I was excited to learn about, but I was actually playing with these things. For those of you that may not have seen this before, this is a weather balloon and what's called a radiosonde, that little white box at the bottom, and it gives readings of temperature and humidity, et cetera, as the balloon goes up through the atmosphere. Now, that wasn't what I thought I wanted to study. I wanted to study astronomy and not meteorology. But it turned out that there were some pretty interesting connections between the two. And from that work, I actually published my very first paper, which was using that radiosonde data, that weather data, to be able to understand how the atmosphere changed the signals, the radio signals that were coming from the stars, so we could make more precise maps of it. So this kind of brings up this notion of flexibility. Sometimes you're given an opportunity to pursue a problem. It may not be exactly what you want, but it's interesting. And in the process of working on it, it's going to teach you something. So be a little flexible. Anything is interesting if you look at it closely and carefully enough. And this was a good example of that. And I eventually got around to doing some work in astronomy. I even got to publish, my first paper in college doing astronomy. But that paper used the data and tools that I developed in that first paper to make the observations even better. Then I went off to college and, went off to graduate school. And was interested in finding a thesis that would kind of combine my interest in medicine at the time with my interest in imaging and technology. And this again was an opportunity to kind of put that action of seeking a mentor into practice. I had done some master's degree work in one domain. It was interesting, nice professors, but not a domain that was going to, I thought, really go forward. I spoke to several other professors, all very nice, but not really the right connection. Finally made the connection to this fellow. His name was Ian Pikett. He was a graduate student of the Nobel Prize winner, Peter Mansfield. So I kind of feel very fortunate to be in that same lineage from Sir Peter to Ian, from Ian, to myself. And he was a great mentor for me. But sure enough, halfway through my graduate career, he left to form a company. Now, that actually turned out to be a good thing because the company he formed was the first company to develop the echoplanar imaging, the very high-speed imaging tools that we use today for most of our functional brain mapping. But as a grad student, have your advisor leave halfway through, that was a little tricky. But again, very fortunate, kind of sought out, somebody that could kind of fill his place, and very fortunately made the connection to the fellow to his right, Tom Brady, who became an outstanding mentor to me for many, many years, both for my graduate work and all through the early phases of my career. And so maybe this highlights this preference for disorder. It was certainly disruptive to lose your thesis advisor halfway through, but you adapt to it. And as it turns out, because Tom's background was more strongly clinical than Ian's, I think the benefits I got from having both of those actually ended up enhancing the kinds of things I was able to learn as a grad student. Well, the other kind of lesson that I'd like you guys to think about, even at this very young stage, if you're in high school, and certainly for the more senior students or graduate students, is that it works the other way around. The way to pay it forward, if you will, is to be a good mentor. And of course, that's not only great for the students and colleagues that you'll be mentoring, but I can assure you it will be at least as good for you, maybe even better. A wonderful example of this is my colleague, Jack Beliveau. So Jack, I suppose, is the ultimate example of the divergent thinking. The picture on the right was not really an exception with Jack. You would always see him trying something new, doing something different, thinking in an unusual way. But, while, of course, I've been super fortunate to have been involved in kind of the birth of functional imaging, and it's such an important tool for our laboratory, it was really Jack that was the guy that brought that to me. I was his advisor. He was my student. And yet the notion of let's focus on a way to image the brain working came from Jack to me and not the other way around. And of course, that inspiration led to this wonderful work that Jack did and did with many colleagues here. That very first functional MRI picture was inspired by the student to the mentor and not the other way. So lots of benefits to this paying it forward. And even in high school, help the students around you. If you're a senior, help the juniors when you go off to college. Be a mentor to high school students like yourself that could use some encouragement to get to where you're going. Kind of a corollary to that is this notion of kind of never saying never, never give up on ideas till you really know whether they're going to work. And the key is, we're scientists, you have to actually do the experiment. There are a lot of people, just like that first little slide that I showed, that will say it can't be done, or maybe shouldn't be done. But in the end, if you think it's important, you should do it. And I think really in my mind, the ultimate example of that is the work of this gentleman on the left side of the picture on the right. That's Ken Kwong. Many people told him that this experiment wouldn't work. He had to work at it many times to get it to work, and yet came up with this completely remarkable conclusion that you could use an MR system just by itself without having to inject anything, radio tracers or contrast agents, just use the brain's own biology to teach us how it was working and even when it was working. A really remarkable discovery that came from the fact that he just wasn't daunted by the fact that people said this wasn't going to work. He went out and did the experiment and did it until he got it to work. By the way, not the only time he's made that leap, just a great example of that. Well, okay, so I think that's enough of me and my background, but I was also asked to spend just a few minutes, and I am mindful of the time, Caroline, that to talk about the mission of the Martinos Center. So there's the statement of our mission. We want to revolutionize imaging for the advancement of science and medicine. We want to inspire people. We want to educate them, as the summer program, of course, is showing, and inform both our fellow scientists and the public more broadly. So underlying this, is kind of a fundamental hypothesis that I've come up with, which is that great tools to see lead to great discoveries. And of course, now I was an astronomer, so you might imagine the example I would come up with is from astronomy. This is Galileo Galilei, and that was his very first telescope, a primitive affair, far exceeded by any inexpensive pair of binoculars you could buy today. But with that, he was the first to actually see sunspots on the sun. He was the first to see the craters on the moon and describe the features of that. He showed the stars and clusters within the Milky Way and star clusters. And in his observation of the moons of Jupiter, really changed the fundamental way that the world saw the Earth's place in it by understanding that the moons going around Jupiter were the same as the Earth and the rest of the planets going around the sun. So he was the one that really took us from the geocentric view of the Earth to the heliocentric one, the one with the sun in the center. So this simple tool led to amazing discoveries. And there's this really nice quote from a famous physicist, Freeman Dyson, that talks about the importance of tools, that he says every time we introduce a new tool, that's what leads to new and unexpected discoveries, because nature's imagination is richer than ours. We need these tools, and those tools lead to the discoveries. And that's kind of what the Martinos Center is about. So not so long ago, we had a retreat of our faculty, And we posed the question, like, what are the core values of the Martinos Center? What do we think is important? And we came up with this list: diversity, innovation, collaboration, passion, integrity of our work, and the freedom to kind of pursue it. And I just thought I'd spend a minute or two and giving some examples of how these core principles actually play out in our world here at the Martinos Center. So the first is diversity. If you just look around the center, and this is where the heartbreak of COVID for this experience is so sad, because had you had the opportunity to walk around the center, just by looking at the faces of the people you met, you would have realized that in order to be a world-class center, you really have to draw from the entire world. And it's a tremendous source of richness and strength and pride, frankly, that 70% of our center were born outside the US. Nothing wrong with the US, but the world's a big place. And we get tremendous strength from bringing all of these perspectives to bear. But of course, it's not just the people that we have at the center that are diverse, but it's the studies and the ways we study, the tools that we have, everything from optical imaging to magnetoencephalography, brain stimulation with cortical stimulation and TMS, molecular imaging with PET and optics, high field imaging, low field imaging. And of course, while these are all examples from our studies of the brain, we also study the heart and the liver and cancer and the musculoskeletal system. We really can study almost anything that we can find a way to take a picture of and learn about. And from that, we can learn about anatomy and physiology, metabolism, chemistry, electrophysiology. The center's strength, I think, is the diversity of perspectives that it brings to the scientific problem, as well as the diversity of the people that are there. Well, innovation, another one of these core values, think different. This is a picture, a really nice one. It came from a popular science article, DIY MRI, do-it-yourself MRI. And this is our colleague, Matt Rosen, who decided, instead of making bigger and bigger magnets, going to higher and higher magnetic fields, he would actually see what happens at the other end, and actually built a system at low field, so successful in its principle that it was commercialized based on his help and a company that he started. And now there's actually images in patients right at their bedside. So an MRI scanner that they don't go to the radiology department, the radiology department goes right to the bedside. And now taking really remarkable pictures that I guarantee you people would have said were not possible at this quality until he and his colleagues set up and say, let's go and do it. And it doesn't stop there. Colleagues like Larry Wald and Clarissa Zimmerman-Cooley are thinking even more different, developing systems like an MR cap, almost more like a tricorder, or something that you can hold on your hands rather than a scanner. Just really pressing the limits, thinking in all directions in terms of where the technology could go. Collaboration, another one of these core values of us. So, I was trying to think of a way to articulate this, and our colleague Gary Boas actually went on to the Harvard Catalyst website and showed the network of interactions between our senior colleagues and the people around them. Here's Larry Wald's network of interaction, people that he's published and worked with. In green are people within the MGH, and blue are people from outside the MGH. Julie Price, who does PET imaging, another dense network across the institution and across institutions. Bruce Fischel, who does computational neuroanatomy, the same. Marie Franceschini, who does optical imaging, the same. Peter Caravan does molecular imaging in the body, the same. Matt Rosen, we just talked about. Jayashree Kapathy-Kramer, who does AI work, the same. All of these colleagues work and do brilliant work because of their dense networks of collaboration. Well, passion, I think if you meet the faculty, the fellows, the students within our center, I think that passion comes through. I just love this example that Mari Franceschini and her colleagues have showed. They're taking their optical imaging and moving it into the most challenging populations, into the tiniest little neonates, premature babies, or taking their systems to West Africa to study childhood nutrition and how that affects brain and brain function. it takes passion to make the effort to do that, and they certainly have it. And finally, freedom, the freedom to develop new collaborations. This may be more for our own colleagues, these new centers that we've set up, David Salat, Steve Stufflebeam with the Institute, the Interdepartmental Brain Center, Peter Caravan leading the I3 Institute for Innovation Imaging. The floor plans just show we're expanding based on our ability to collaborate with others. And then our individual scientists, Marco Logio is setting up a new collaboration with anesthesia in a pain and neuroinflammation center. Vitaly Napadal is actually moving to Spalding Rehab while keeping his appointment here with us. So he's not leaving, but he's expanding a new pain center with the Spalding Rehab Hospital. Jacob Hooker, who runs our neurochemistry efforts, now is the scientific director at the Lurie Center, connecting to the Mass General Hospital for Children. So great examples of the freedom that our investigators have to pursue these collaborations across the enterprise. The final one, and I know I'm out of time, is integrity. And I really, was struggling, like, what's the slide? What's the picture to go with integrity? Not really sure I had a great one. I'm happy for somebody to suggest one for me. But I guess the bottom line is it does have to be a part of everything we do. As scientists, of course, there has to be the integrity of our data. But there's integrity in how we interact with each other as scientists, how we interact with our students, with our mentors, how we interact with our staff, our broader colleagues around us within the institution, and our colleagues across the community and across the public. And I'd like to think that the members of the Martinos Center keep that in their hearts and show that in their actions all the time. So with that, I think I can stop sharing, turn the screen back. It says 10:31 on my clock, so I'm a little late, but not too late.
That was pretty good.